Hi everyone, this is You Can Find Geodesic Paths in Triangle Meshes by Just Flipping Edges. I'm Nick Sharp, and this is work with Keenan Crane. Geodesics are paths along a surface, which are straightest or locally shortest curves across a shape. These paths are widely useful for modeling, mesh generation, analysis, and more. In this work, we discovered that a simple edge flipping strategy can be used to compute these geodesic paths. The input to our algorithm is some path along the surface of a mesh which you wish to straighten, or more generally, a loop or a curve network along the shape. The output is a geodesic path, which intuitively corresponds to pulling the curve tight. Our algorithm also generates an intrinsic triangulation containing that path, which is useful for many tasks in geometry processing. Our new perspective allows us to construct geodesic curves on surfaces well suited for a variety of applications. We'll see examples including cut graphs and segmentation networks, as well as finding Bezier curves, and even using geodesics as boundary conditions for PDEs, thanks to a new notion of constrained triangulation enabled by our approach. The big idea of our algorithm is simple enough to describe in a single slide. We're going to flip edges to create geodesic paths. So suppose we have some path, which I've marked here in red, that isn't yet a geodesic. Our basic operation is to pull the curve tight in this local neighborhood, yielding a shorter version of the curve. Remarkably, this can be done with a simple sequence of edge flips. After the flips, we just slide the curve over to be a new, shorter version of itself. Applying this procedure repeatedly eventually yields a geodesic. We show that this procedure always works, even on curved surfaces. There's been a great deal of past work on the subject of finding geodesics. Most methods fall broadly into two categories: window-based methods, which expand an outward search to find geodesics, and iterative straightening schemes, which repeatedly shrink some Lagrangian representation of a curve. One cool thing about our approach is that we have a very different take on the subject. We find geodesics by flipping edges. Furthermore, our algorithm offers new properties that are quite useful in practice. It guarantees that no new crossings will be created by the straightening process, and it also generates this triangulation which contains the geodesic that's super useful for downstream tasks. When I say geodesics, you probably think first about shortest geodesics, but generally there are lots of geodesics other than the shortest one. A geodesic is more like a straight line or just a locally shortest path along a surface. Globally shortest geodesics make a lot of sense when measuring distance, but not quite as much sense for other applications, mainly because there's just one of them between any 2 points. There have been a lot of well-known algorithms for computing geodesic distance and shortest geodesics, but due to the global nature of the problem, these algorithms tend to be pretty expensive. We work more generally with the larger space of all geodesics, which might only be locally shortest. And these are really good for manipulating curves on surfaces, in a large part because there's many possible solutions. There are a lot fewer and less well-known algorithms for finding these geodesics, and they actually turn out to be quite computationally cheap. To expand on one key difference of our method from past approaches, our algorithm guarantees that no new crossings will be introduced by the straightening process. Or, being a bit more formal, we find a geodesic in the same isotopy class as the input. Now, because we take this non-crossing perspective, we do make the assumption that the input curves themselves are already non-crossing curves. This is a very important and common setting in practice. Suppose we wanted to straighten a network of cuts in order to fabricate patches for this chair. It's crucial that we not introduce any new crossings, or we would lose the notion of patches on the surface. The key tool that makes all of this work on curved surfaces is intrinsic triangulations. The basic idea of intrinsic triangulations is to represent geometry not by vertex positions, but by edge lengths. So while usually we might store for a mesh its connectivity as well as a position associated with every vertex, we're going to throw away those positions and just store a length associated with each edge. This representation is important because it allows for a large space of triangulations of a particular shape, all of which exactly represent the original underlying geometry. We'll traverse the space of interesting triangulations using intrinsic edge flips. When flipping an edge, we consider two adjacent triangles, forming a diamond, and we replace the diagonal with the opposite diagonal by updating the mesh connectivity, as well as computing new edge lengths. This is really a simple and efficient operation to evaluate. The key fact about these intrinsic edge flips is that they exactly preserve the geometry of the underlying surface. So whenever I talk about edge flips, we mean this intrinsic edge flip on the right, certainly not this extrinsic edge flip, which would be distorting our shape. As we flip many edges, we'll be implicitly constructing these long bent triangles along the surface. But it's important to remember that we won't need to explicitly represent how these triangles lay across the surface. the representation is always just a fixed amount of data for each edge, and the core of the edge flip is just a simple constant time operation. In the past, these edge flips have been used almost exclusively to find special Delaunay triangulations, but here we're going to use them for something totally unrelated to the Delaunay property. You'll notice that as we do these edge flips, the edges of the triangles become little geodesics across the surface, so this might give you some idea why they're useful for our algorithm. One other thing to note is that these edge flips can create what's called a delta complex, for instance by creating an edge which connects a vertex to itself. This is a bit scary and makes formal proofs a lot more complicated, but in practice it won't affect our algorithm at all, and we can still use standard data structures like half-edge meshes. So with that machinery in place, let me tell you just how you can find geodesics solely by flipping edges. We're going to depart from the norm a little bit and represent curves only as sequences of edges in a triangulation, more like in a graph theory sense. And when I first say this, it should sound way too restrictive, like we'd never be able to find geodesics. But remember that with intrinsic triangulations, we can change the edges, so there is hope. To be precise, our algorithm will take as input a path along the edges of a mesh, or more generally, a loop or curve network along the edges of a mesh, and it will shorten it, pulling it tight to produce a geodesic edge path, again along the edges of a mesh. This path will be isotopic to the input, which essentially means that it can be continuously deformed from the path you started with. And in particular, it's going to be the sequence of edges in a mesh, or really an intrinsic triangulation, which will turn out to be a really useful property, because we can use this triangulation for other tasks. The edges of intrinsic triangulations are already always geodesics. So to find geodesic edge paths, we really just need to worry about what happens at the vertices where these edges meet. At any such vertex, if the swept angles on either side of the path are greater than pi, then the path is a geodesic at that vertex. And this definition is consistent with past algorithms like MMP. Our approach is basically then just a greedy procedure that says at any vertex where this property does not hold, where the path is not yet a geodesic, we can perform some local edge flips in order to introduce a shorter path. Our main subroutine is what we call the flip out procedure, because it literally flips out the edges in a vertex ring in order to create a shorter path. In particular, consider some vertex in the path, which is marked here in red, where the path makes an angle sharper than pi. The flip out algorithm is then just to repeatedly flip any edge that can be flipped in order to remove it from this neighborhood. Algorithmically, this means that whenever these outer angles beta is less than pi, we just flip the corresponding edge. And that's it. When this procedure terminates, it's guaranteed that the path along the outer perimeter will be shorter than the path we started with. To step through this, we start out with some initial path, which isn't a geodesic because it makes a turn. We notice that this first angle is less than pi, so we flip the edge. The next angle is greater than pi, so we don't touch that edge. And this last angle is less than pi again, so we flip the edge, removing it from the neighborhood. After this procedure, we can update the path to be the path along the outer perimeter, which is necessarily shorter than the path that we started with. We prove that this will always be the case, even on curved surfaces. Applying the flip out subroutine can always flip edges about a vertex to introduce a shorter path if the path is not yet a geodesic. This takes a few facts. First, we prove that you can always flip the edges you need to flip, which basically follows from the preconditions of the algorithm. We prove that the procedure always terminates, that you don't get stuck flipping edges forever, which you can see because each flip basically removes an edge from the neighborhood. And finally, we prove that when you perform all these edge flips, you're left with a triangulation such that the path along the perimeter is shorter than the path you started with. This follows because once all these angled beta are greater than pi, the curve along the perimeter is a convex curve. And then by some classical planar geometry, the containment of convex curves, we know that it must be shorter than the outer curve we started with. Now, I mentioned earlier that these edge flips can create a delta complex. And this makes our proofs quite a bit more complicated. I won't go into details, but in particular, proving termination becomes a lot more nuanced. A big part of our technical contribution is extending all of these proofs to the general case of a delta complex. And the good news is that everything works out exactly as you would expect it to in the end, and you can use our flip out procedure just as we stated it initially in order to always straighten a curve and find a geodesic. Once we have this basic subroutine, we can just apply it repeatedly until any curve of interest is a geodesic. Here we do this for paths, as well as for loops on surfaces. For loops, there's one small extra case you need to handle, but I'll refer you to the paper for details. One more thing to note is that although a purely intrinsic representation is sufficient for a lot of applications, we'll often want to output a geodesic as a polyline across the surface, for instance, to visualize it. In that case, we need a little bit more data than just an abstract list of edge lengths as our ultimate output. To do this, we use the signpost data structure, which tracks, in addition to the length, the direction of each edge. Then, at the end of our algorithm, to recover the actual path that the geodesic takes across the surface, we just need to trace out one of these edges, which is a fast and cheap operation. Our algorithm can be seen as a kind of discrete, curve-shortening flow on a surface. As expected, in a convex region, it'll contract a loop to a point, like we see here. Also, you can set alternate stopping criteria, such as a length threshold, which stops the curve from changing too much. The new flip-based perspective has a lot of practical value. It's guaranteed to find an exact geodesic in a finite operations, and in practice, the runtime is generally just a few milliseconds. More importantly, if you find an initial path by running Dijkstra's algorithm between 2 points and then straighten it, the straightening will be up to 10 times faster than just the Dijkstra search on average. Straightening a path is so fast that it's probably negligible compared to whatever else you're already doing. Robustly implementing geodesic algorithms in floating point is notoriously difficult in practice. Even standard libraries like Seagull struggle with hard inputs. Fortunately, we find our scheme to be quite robust, with a 100% success rate on non-degenerate meshes across several large datasets. Of course, robustness is really a property of the implementation as much as it's a property of the algorithm, but our algorithm requires just one pretty simple geometric operation, the edge flip, so it's in a good position for robust implementation. Once we can straighten curves, we can take it farther and also use a simple de Castelgau-style subdivision procedure to find Bezier curves along the surface. As always, all of the curves you see here are edges of an intrinsic triangulation, which I haven't drawn. We can also make the jump to straightening networks of curves and loops along edges, which show up very frequently in geometry processing. For instance, when cutting a shape to flatten it, we can easily make the cuts geodesics rather than jagged paths along the input edges. Or we can straighten the boundaries of a segmentation to be nice, smooth curves. The key property of our algorithm, which makes it uniquely well suited for these tasks, is that it provably guarantees that the topology will not change. And that's really necessary for these applications to make sense. You might have noticed that as we do these edge flips in our algorithm, we can and do create extremely skinny triangles in the triangulation. These skinny triangles don't affect robustness. Some intuition for why is that they're no different from the skinny windows which already appeared in past approaches. Fortunately, if we want to compute with the triangulation afterwards, we can just do some quick Delaunay refinement to improve its quality. This allows us to serve as a missing link to perform constrained triangulation on surfaces. In the plane, it might be common to take a set of points and lines, find a conforming triangulation, and then refine it to get a high-quality mesh. Well, recall that our algorithm generates as a byproduct a triangulation containing the geodesics, so it can serve as a surface analog of this procedure, where we take some network of points and paths, find a triangulation corresponding to the geodesics amongst them, and then generate a high-quality version of the same mesh. This makes it easy to do things like use geodesics as boundary conditions for PDEs, where up top we generate a cross-field aligned to some geodesics, and down below we solve a Poisson problem which takes Dirichlet boundary conditions from a Bezier curve on a surface. Before we wrap up, we can take this one level further. Thus far, I've been focusing on cases where we shorten some given input curve, but we can also adapt our algorithm to finding geodesics emanating from a source to every other vertex in a mesh. The strategy is just to constantly apply the flip-out subroutine on the frontier of a Dijkstra search. This is still just a local algorithm, not guaranteed to find globally shortest geodesics, but it's very fast and effective in practice. It's amazing to me that we can construct a single triangulation that simultaneously contains geodesics from a source to every other vertex in a mesh. And finally, reading off the angle of those edges yields a discretization of the polyhedral log map. It's really promising to see that the basic flip-out subroutine can be mapped to other variants of the problem. Wrapping up, we saw a new algorithm for finding geodesics which uses edge flips. It's guaranteed to find exact, non-crossing geodesics and applies broadly to paths, loops, networks, and so on. It has many applications in geometry processing due to its particular properties. There's still a lot to explore. In particular, we'd hope to use exact predicates to yield further robustness guarantees, as well as adapting the algorithm to shortest geodesics. From a higher level, we've shown that it's possible to use intrinsic triangulations to lift classical geometry routines from the plane onto surfaces, and I'm optimistic to continue that line of research. This algorithm is available in several different code forms, including a core implementation in Geometry Central, as well as a demo with a GUI you can play around with. So please check it out and let us know what you think. Thank you.